Hi, I am Sanjay Patel. In this video, I am going to prove the formula for nth order derivative of the power of a binomial expression. And then we'll derive some interesting consequences from this formula. So let us begin with this very important nth derivative formula for the binomial expression. We already derived some nth derivative formula for some standard functions. So the next one is this theorem. If y is equal to ax plus b raised to m, ax plus b raised to m, where this m is a natural number in this case, then prove that the nth derivative yn is equal to m factorial upon m minus n factorial into a raised to n into ax plus b raised to m minus n. And this is true for every n belongs to n with n is less than m, where n is less than m. Okay, means this formula is valid only when the order of the derivative is less than the power m here. Okay. And one more thing is that it is valid only for m belongs to n, means m must be a positive integer, because we can define factorial only for integers, positive integers. So let us begin the proof of this using the mathematical induction as we have discussed. So whatever we want to prove by induction, that statement we call as P of n. So this yn formula we want to establish. So let us consider P of n as yn is equal to m factorial upon m minus n factorial into a raised to n into ax plus b raised to m minus n. And note that here this n is less than m. Okay, so the first thing we do is we verify the result for n equal to 1. So we take n is equal to 1, and what is our aim is to prove that this result for n equal to 1 is true. Means we want to find y1, and y1 means the first derivative of this given function. Y is equal to ax plus b raised to n. So I start this way. We have y is equal to ax plus b raised to n. Okay, so we differentiate this with respect to x. Differentiate with respect to x, we get dy by dx, that is y1 here, and derivative of this thing, something raised to m, is m into something raised to m minus 1. So I can write m into ax plus b raised to m minus 1, that is first thing, into the derivative of this ax plus b using the composite function rule, it is a. Okay, it is very simple. You know how to find derivative of 2x plus 3, for example, 2x plus 3 raised to 7. So it is as simple as that. Now this we want to rewrite in a different way so that we can compare with this. This m I can replace by m factorial upon m minus 1 factorial, because you know that so if you want to write 8, you can write as 8 factorial upon 1 less, that is 7 factorial. 8 factorial means 1, 2, 3 up to 8, and 7 factorial is 1 to 7. So we can write like this. And this a raised to 1 is also there, into ax plus b raised to m minus 1. So if you put n equal to 1 in this formula, you will see y1 is equal to m factorial upon m minus 1 factorial, a raised to 1, ax plus b raised to m minus 1. So therefore, P1 is true. Therefore, P1 is true. Now let us assume that Pk is true. So suppose Pk is true. What is the meaning of Pk is true? That is, we have for some k belongs to n, yk is equal to m factorial upon m minus k factorial a raised to k into ax plus b raised to m minus k. Let us call this as result number 1. What we have done is just we have put n equal to k here, and we have written that p of k is true, this statement pk. Now, to prove pk plus 1 is true, we have to find the next derivative of this yk, that is yk plus 1. So, we differentiate this with respect to x. So, let me write here, differentiate result number 1 with respect to x on both the sides. So left hand side will be yk plus 1. The next derivative of yk is yk plus 1. Now this part is constant here. So I will write it as it is, m factorial upon m minus k factorial into a raised to k into derivative of now this ax plus b raised to m minus k can be obtained using the formula x raised to n, which we know as n into x raised to n minus 1. So I can write m minus k into ax plus b raised to m minus k minus 1. And again derivative of ax plus b is to be written over here, that is into a. Derivative of ax plus b is only a into 1 plus 0, so it is a. Further simplifying this, you observe that here we have m minus k and here m minus k factorial. Something like, if you take, suppose this is as 8 and this is 8 factorial, then 8 upon 8 factorial will be 1 upon 7 factorial. So I can write it as m factorial upon 1 less than m minus k, that is m minus k minus 1 factorial, and then this a raised to k into a will give you a raised to k plus 1, okay, into, remember we have cancelled this with this and we get m minus k minus 1 factorial, and what remains is ax plus b raised to m minus k minus 1. So this proves that yk plus 1 is m factorial upon m minus k plus 1 factorial into a raised to k plus 1 into ax plus b raised to m minus k plus, I can write like this, let me remove m minus k plus 1. Okay, so this proves that p of k plus 1 is true. If you substitute n equal to k plus 1 in that p of n, you will see that this is the required result. So therefore, we can say p of k plus 1 is true. Okay, so thus p of k implies p of k plus 1 is true, and therefore p of n is true for every n belongs to n. Okay, and that is, we have yn is equal to m factorial upon m minus n factorial into a raised to n into ax plus b raised to m minus n for every n belongs to n. Remember, this formula we can use only for m belongs to n, and the value of m must be greater than or equal to n. Okay, fine. And from this, let us derive some corollaries. And before we derive the corollaries, let us note one consequence or conclusion from this formula, and let me write as a note. The first thing you want to note is if y is equal to ax plus b raised to m, where m is a natural number, then the nth derivative yn is given by, see, this formula we have proved only for m greater than or equal to n. Let us discuss what happens if m is less than n, okay, or you can say other words n is greater than m. That we'll discuss here. So first of all, the formula, as we told, that it is valid for m less than or m greater than or equal to n. So first I am writing the formula as it is: m factorial upon m minus n factorial a raised to n ax plus b raised to m minus n. This formula we can use if the value of say n is strictly less than m, or you can say m is greater than n, both are same. What happens when n and m are same? See, n is the order of derivative and m is the power of this binomial. Here power is a positive integer, okay, and n is also a positive integer. So there are three possible relations between n and m, that n can be less than m, or n can be equal to m, or n is greater than m, okay. So for this, if n is equal to m, what we'll get in this formula? Can we put n is equal to m here? Let us see. If n is equal to m, this is n factorial, this is n minus n 0 factorial. So 0 factorial is 1, as we know, so there is no problem. Here a raised to n as it is, and ax plus b raised to n minus n, that is 0. So x plus b raised to 0 is 1. So we'll get this thing, n factorial into a raised to n. You can verify. What you will get is this. Let me explain here. If I put m is equal to n, so n factorial upon n minus n factorial into a raised to n into ax plus b raised to 0. So this is 1 and this is 0 factorial, so it is also 1. What we are left with is this only, n factorial into a raised to n. Okay, fine. So that is the second possibility. But if n value is greater than m, what does it mean? That is, if the nth order, the order of the derivative becomes larger or greater than the value of this this exponent, that is m, okay, in that case the derivative will be 0, because what is this ax plus b raised to m? Ax plus b raised to m is a polynomial. It's a polynomial of degree m. And if you take derivative, if you keep on taking derivative of this polynomial, then the order of the derivative, when it exceeds m, the derivative becomes 0. Let us understand this by one simple example. Suppose I have a polynomial y is equal to x cube. Okay, let us consider this way. So its first derivative, that is y1, is 3x square. Second derivative y2 is 6x. Third derivative y3 is 6. And the fourth derivative is 0. Fifth derivative is also 0, and so on. So this 4, the order of the derivative is greater than the degree of this polynomial. Okay. So for any polynomial, not only for x cube, just remember, if p of x is a polynomial of degree, say m, then the derivative of order which is greater than this m is always 0. So if you have polynomial of degree, say 10, then the 11th derivative or 11th order derivative of that polynomial will be 0. And if you take the derivative of the same order as the power of the polynomial or the degree of the polynomial, then the value, the derivative is always constant. For example, you can see here the third derivative. So these three and these three are same. So when the order of the derivative and the degree of the polynomial both are same, we always get a constant like this. So this is very, very important thing, remember. Okay, now we are going to derive some corollaries based on this important formula. So one more thing I want to tell you before I start. This is our number 1, and number 2 is this formula I can rewrite for n less than m in a different way. Say yn is equal to m factorial upon m minus n factorial a raised to n ax plus b raised to m minus n. Okay, this we are simplifying as, say, this m here in this case is say less than in this case I am taking n is less than m. Okay, if n is less than m, this m minus n appears somewhere in this product. So I can write this as 1 into 2 into 3 up to, say, m minus n. The next step will be m minus n plus 1, m minus n plus 2, and we go up to m, and the previous term will be m minus 1. Okay, and this divided by m minus n factorial, and the remaining thing is as it is, a raised to n ax plus b raised to m minus n. Okay, now this first the product of the first m minus n numbers, that is nothing but m minus n factorial. So this part gives you m minus n factorial, and this will be cancelled with this m minus n factorial. So what you will get here is only this thing, that is, I am writing in this order, the reverse order, m minus 1. I am writing in this reverse order, m into m minus 1, m minus 2, up to m minus n plus 1 into a raised to n into ax plus b raised to m minus n. So if you simplify like this, what we can understand here is, even though m is not a natural number, we can use this formula here. And in fact, it is true. We are not going to prove the result, but just we assume the result without proof. And it is if y is equal to ax plus b raised to m, y is equal to ax plus b raised to m, where m is any real number also. If m is any real number or a rational number or anything, then yn is given by m into m minus 1 into m minus 2 up to m minus n plus 1 into a raised to n into ax plus b raised to m minus n for any n belongs to n, for every n belongs to. Remember, n is always natural number because n is the order of the derivative. Okay, that I cannot take as fraction here. So this is another or a more general formula which we remember as our second remark. Okay, so now you can use this formula. Suppose you are given a power like this of ax plus b. If y is equal to, say, if you have 2x plus 3 raised to 1 by 2, you can use this and find, say, for example, if you want to go for the third derivative, so you can find y3 by this way. M is 1 by 2, so 1 by 2, then 1 by 2 minus 1. Okay, and here we put n is equal to n is equal to 1, n is equal to 3. So this is 1, 1 by 2, and this is 3, and this is plus 1. So minus 2, minus 2 plus 1 by 2, minus 2 plus 1 by 2. So that is minus 5, no, 3 by 2. Yes. Okay. So we have to go up to this step, minus 3 by 2. So 1 by 2 minus 1, that is minus 1 by 2. 1 by 2 minus 2. Okay. So that is minus 4 plus 1. So minus 3 by 2. So we stop here. And then a raised to n. What is a here? A is 2. And 2 raised to n means n is 3. And then 2x plus 3 raised to m minus n. That is 1 by 2 minus 3. So this is the third derivative of this 2x plus raised to 1 by 2. So this way you can use the formula for any value of m which is not necessarily a natural number. Okay. Now let us derive some consequences from this very important formula which we have written here for, say, real number. So the first formula here I want to write is as a corollary number 1. If we take, let me write directly. See, what I want to prove here is if y is equal to ax plus b raised to minus m, okay, then y is equal to ax plus b raised to minus m, then we can get this formula as yn is equal to, if I put minus m here everywhere, what I will get, that I will explain first. If I put m equal to minus m, what we will get is yn is equal to minus m, then minus m minus 1, minus m minus 2, and so on, minus m minus n plus 1 into a raised to n into ax plus b raised to minus m minus n, like this. Okay. Here there are n brackets, and from each bracket if I take minus 1 as a common factor, then we can get minus 1 minus 1 minus 1 n times. So minus 1 raised to n, and what remains is m into m plus 1, because if minus 1 is taken common, here you get m plus 2, and so on. Finally, if I take minus 1 common from the last bracket, I will get m plus n minus 1, okay, this thing, into a raised to n into ax plus b, okay, raised to minus m plus n, like this. So we have this formula. When m is negative, we can use directly. So yn is equal to minus 1 raised to n in m into m plus 1, m plus 2, up to m plus n minus 1 into a raised to n into ax plus b raised to minus m and minus n. And this is also true for every n belongs to n, but m can be anything. Okay, here m can be anything. M is any real number, or let me take simply m is a constant, any constant. Okay, so this is just a simple explanation how this can be obtained. There is no proof, it's just putting this way. The next result, which is more important, is corollary number 2, and we want to prove this if y is equal to 1 upon ax plus b. If y is equal to 1 upon ax plus b, then yn is equal to minus 1 raised to n into n factorial into a raised to n upon ax plus b raised to n plus 1. you want to derive this formula, which is very, very simple. So proof of this corollary goes like this. We have this formula in corollary 1. So in this above result, that is in the corollary number 1, we put simply m is equal to 1 because it is valid for any real number. So I can take m is equal to 1 here in this corollary. Okay. So we get say y is equal to ax plus b raised to minus 1 here, and that implies the nth derivative yn is minus 1 raised to n, then 1 into 2 into 3 up to n. Putting m equal to 1 here, everywhere. Okay. So we get 1, 2, 3 up to n into a raised to n into ax plus b, and putting m equal to 1 here, we get minus 1 and minus n. And this formula now I can write in a different way as y is equal to 1 upon ax plus b, because ax plus b raised to minus 1 is 1 upon ax plus b, and yn is minus 1 raised to n. Now this becomes n factorial, so I'm writing n factorial here, into a raised to n, and this ax plus b raised to minus 1 minus n I'm taking in the denominator, so I can write it as ax plus b raised to n plus 1. Hence this is proved. Okay, so corollary number 2 is proved. There is one more interesting consequence which follows from corollary number 2, and that is about derivative of, or nth derivative of log function. So let me write that as a corollary number 3. If y is equal to if y is equal to log of ax plus b to the base e, then prove that its nth derivative or nth order derivative is minus 1 raised to n minus 1 into n minus 1 factorial into a raised to n, n minus 1 factorial into a raised to n upon ax plus b raised to simply n. Okay. See, to remember this formula for log function, it is what you have to do is just replace n by n minus 1 in this right hand side, except in this a raised to n. Okay. See, so you will get minus 1 raised to n minus 1, n minus 1 factorial, and n minus 1 factorial, and here you will get ax plus b raised to n. Fine. Okay. But how to derive this formula? So we prove this way. It is very simple. Consider y is equal to log of ax plus b. This is given to us. Okay. This is given to us. Here we have y is equal to log of ax plus b. We differentiate this with respect to x. So I will get dy by dx, that is y1, and the derivative of log of something is 1 upon something, that is 1 upon ax plus b, and in derivative of ax plus b is a. Okay. So we get this formula, which is in the corollary number 2. I mean this function 1 upon y equal to 1 upon ax plus b. It is the same function, and this constant is there in the multiplication. I want the nth derivative of this y is equal to log of ax plus b. But here I am having only the first derivative. So still I need to find n minus 1 derivative more of y1. If I take the n minus 1th derivative or n minus 1th derivative of y1, what I will get is yn. For example, suppose I want to find y10, okay, and I have found only the first derivative y1. Then what how many times we have to differentiate this y1? So it is 9 times. So if I take ninth derivative directly, ninth order derivative, what I will get is y10. So it's the same thing. So if you take n minus 1th derivative of y1, you will get yn. So let me write this way. Taking n minus 1th derivative, on both the sides, what we get is y1 n minus 1. This is the standard way of writing this way. A is a constant, so it will not disturb us. So we write 1 upon ax plus b, and we have to also find the n minus 1th derivative of this thing, n minus 1th derivative. We know that n minus 1th derivative of y1 is yn, as I explained here, and n minus 1th derivative of 1 upon ax plus b. For that, you can use this formula, because this formula gives how to find derivative of 1 upon ax plus b. So in this formula, we have to put only n equal to n minus 1. Okay. So just putting n equal to n minus 1 in that formula, what I will get is minus 1 raised to n minus 1 into n minus 1 factorial a raised to n minus 1 upon ax plus b raised to n minus 1 and plus 1, like this. Just I will show that formula again. In this formula, here in this formula, we put n equal to n minus 1 because we want now n minus 1th derivative of this type of function. So y minus 1 raised to n minus 1, n minus 1 factorial a raised to n minus 1 upon ax plus b raised to n minus 1 plus 1. Okay. So simplifying this, what you will get is yn is equal to minus 1 raised to n minus 1, n minus 1 factorial, these two as it is, but this and this makes it a raised to n, and the denominator is ax plus b raised to n. So we get this formula for the nth order derivative of log function. Okay, so what we have put is, if y is equal to log of ax plus b, then nth derivative yn is given by this formula. Okay, so we have derived this important results about nth derivative of power of binomial expression. Let us take quickly one small example. Suppose we have y is equal to, say, y is equal to 2x minus 3 raised to something. Say, if y is equal to 2x minus 3 raised to 7, then find the fifth derivative. Suppose fifth derivative at 2. Okay, this type of question can be asked. Find phi of 2. So first of all, in such problems, what we need to write is the formula, proper formula. We know that we have, for y is equal to 2x minus 3, and let me write the general formula. For y is equal to ax plus b raised to m, the formula is yn for nth derivative. Yn is equal to m factorial upon m minus n factorial into a raised to n into ax plus b raised to m minus n. This we derived in the beginning of this lecture. Okay. Now let us understand and see what is the value of a here, b and the power m. A is equal to 2, b is equal to minus 3, and m is equal to 7. Okay, so we get yn is equal to 7 factorial upon 7 minus n factorial. Then a is equal to 2, so 2 raised to n, and 2x minus 3 raised to 7 minus n for every n. Not for, okay, no problem. So we have this result, this step, and if I want y5, so I can put n equal to 5 here, and what I will get is y5 is equal to 7 factorial upon 7 minus 5 factorial into 2 raised to 5 into 2x minus 3 raised to 7 minus 5. So 7 factorial upon 7 minus 5. 7 minus 5 is 2. So 7 factorial upon 2 factorial into 2 raised to 5 into 2x minus 3 square. This is the answer. And we need to find y5 of 2. So this is our original question. We want to find what is y5 of 2. So this is equal to 7 factorial. Wherever x appears, we put x is equal to, this is the value of x. So we put x is equal to 2 here, and we get 2 to the 4 minus 3, that is 1 raised to 2. So answer is simply this much. Okay, we'll do some more interesting problem at the end of all the results. Now, in the next lecture, we are going to prove very interesting theorem, and that is known as Leibniz theorem, which gives us the method of finding the nth order derivative of product of any two functions. And that is very, very important result. Okay, thank you.